Welcome to a lesson with Dr. Powell. Let's take a look at how the idea of exterior derivative of differential forms, which we've been talking about for Green's theorem and Stokes' theorem, where we take like a df wedge or something like that, how we can think about the process of going from the vector field f to a new vector field g, where we can maybe do a line integral over here and do a surface integral over here. The process of changing your vector, which we've discussed, commonly in textbooks has various names. So for Green's theorem, this process is called taking the curl of a vector. It's often notated as del or gradient cross, or del cross. This means curl. So we would label, we would do this, we'd say del cross, okay, f, and that would be the curl. Notice it makes sense because when we're doing a wedge, it's kind of like a cross product. And then we're also kind of taking a gradient in some sense. When we compute df, we kind of have that in the dot product, popping out here. So the two things combined usually help us think about this as being the curl. Notice that the curl of the vector takes us from a differential 1 form to a differential 2 form for Green's theorem. So another way of stating Green's theorem, at least notationally, would be as follows. You could say dr over c. It'd say that is equal to, where c is the boundary of S, you could say this. We're taking a curl. And maybe this is over the surface of your dA there. Okay, so you can think about this if you want in a way like this, where these are dot products. Okay, so that's a way of stating Green's theorem. Now, also we have for Stokes' theorem, we have a similar thing, but we have a different symbol. Well, use the same basic symbol, but instead of a cross, we take dot, but that's just to remind us that we're really, it looks like almost like a dot product, where if we have in our components of our vector, if we have f, g, h, quite literally we end up with like fx plus gy plus hz kind of. And so in some sense, it's kind of like a dot product happening. In fact, you end up just getting a single scalar number multiplied by dx, dy, dz anyway. And so we use this symbol right here. It's just called the divergence of a vector field. So if we start, for instance, with a surface integral, we can say that's equal to triple integral over the volume, where the surface is the boundary of the volume, of the divergence here. But right, where we have like dv, which is, I think, dx, dy, dz. Now, again, the way you compute this is just by doing the little df wedge thing and the dg wedge thing. And so it's really the same thing. So we have a symbol, this symbol, and we have this symbol, which quite literally have the same mechanics for how they work. It's really the same operation, but we kind of reserve these names. At least this is what's commonly done, like in physics, engineering, and in textbooks and so forth. This one is called the curl. This one's called the divergence, but it's really the same thing being done. This takes us from differential 2 forms to differential 3 forms. This one takes us from differential 1 forms and takes us to differential 2 forms. Thanks for watching.